All right, so today's last speaker for our Fission Week is Dr. Ramona Vogt. She's a staff scientist at Lawrence Livermore National Lab and a adjunct professor in physics at the University of California, Davis. And she's going to tell us about how photon measurements can be used to measure spin of fission fragments today. So take it away, Ramona.
Yeah, thanks. Hopefully that's just at the end. I'm going to be first telling you how we generate fission events to begin with, and that's going to probably take a good amount of my time just to get that far. So you've heard a couple of lectures already this week by your um, stellar lecturers and Kyle and Nathan. Um, so fission is a really complex process. I'm sure you've understood that from what they've said. Um, the nuclear forces underlie all of the interactions that we deal with when we consider fission. But basically, for neutron-induced fission, let's just imagine you have a neutron coming in and it hits um, a very heavy nucleus. Um, it can get it gets it agitated, and it can start changing its shape from, I mean, not all nuclei are spherical, not by a long shot, but just imagine it's a fairly compact configuration, but then the nucleons start moving back and forth, and you get something that looks like a peanut, and then maybe like a dumbbell or barbell at some point, where you have two almost completely formed fragments and a neck in between. And at some point, that neck will snap, and that's called scission. And then you have two hot, excited, rotating fragments that need to lose some of their excitation energy. So um, the mass of a proton is around 940 MeV, so nearly 1 GeV. And when the nucleus snaps like this, it it has about 200 MeV of energy, and that's about 20% of the mass of the proton. That's distributed between the motion of the fragments away from each other, it's the total kinetic energy, and also the excitation energy of the fragments. And that excitation energy is about 10% of that total energy available. Most of it's kinetic energy, but that's enough to make these fragments hot and rotating and excited. And the most efficient way that they can lose their energy is by emitting neutrons. So the first thing that happens is the prompt neutrons are emitted, and then when there's not enough energy anymore to emit neutrons, then photons get emitted, and you get down to more or less the ground state of the nucleus at that point. But then it's still subject to weak decays like beta decay and so on. And you can have delayed neutron and gamma emission, and you can also, by beta decay, you've changed a neutron into a proton, and so you've changed the nucleus from whatever it was that it started out as um, to the next element in the periodic table. So you have, fission is governed itself by the strong force, which also governs neutron emission. Gamma emission is accomplished through the electromagnetic force, and beta decay um, by the weak force. And so we have three three of the four forces of nature involved in a fission event. And the time scales are very different because of that. So fission takes place over a few femtometers, but and that's also about the same time that, for neutron emission, but then gamma emission happens a little bit later, because of transitions and so on. And so that can happen over millisecond, not, I mean, sorry, nanoseconds and so on, or so on. And then the beta decays take place over microseconds, milliseconds, seconds, months, years, depending on the half-life of the nucleus. So it sounds very complicated, right? And yeah, it kind of is. So you need specialized physics models to study fission. And since there's no fundamental theory that can explain the whole process in detail, you really need phenomenology. I mean, I know some theorists like to hold their nose and say, we really want to do real theory. No, we really have to do real phenomenology to be able to track fission, but with as much physics involved as possible. So my collaborator, Jörn Randorf, and I have been developing FRIA, which stands for Fission Reaction Event Yield Algorithm, since 2009 to study fission event by event. And this is the first fission model that was published and made generally available. You can go to Computer Physics Communications and download it and play with it yourself. And basically doing event by event shows how important energy and momentum conservation is for really understanding fission data. I mean, just energy and momentum conservation can buy you a lot. And this is something that was never inherent in any of these models before. So FRIA is fast enough to use on a laptop. You can run 1 million events and not even have time to pour a cup of coffee. So it's a big advantage. I'm not going to talk about any other codes than FRIA, but there are several that differ in the details. CGMF from Los Alamos, FIFRLAN, which is developed in France, and GEF in Germany. These are all, I mean, CGMF and FIFRLAN have similar philosophy to how the event is done as FRIA. GEF is kind of, it sets up the fission in a slightly different way, which makes it rather different from the other three. Before that, the codes were deterministic and based on average events and tuned specifically to agree with some subset of average data. And if you're wondering what this is down here in the bottom right corner, this is Freya. She's a Nordic goddess and she rides in a chariot pulled by cats. The Renaissance putti, these little angels, this is a later version of, I mean, this is probably some Italian version of Freya, except that, she's very modestly clad here. You can find more interesting depictions on Google. So event by event modeling is really efficient for studying fission. And we had the idea to do this because in high energy physics, like high energy nuclear collisions and particle collisions, like proton-proton, there are many different multiple outcomes. So Monte Carlo event generators are used in those cases for studying detector response and predicting outcomes of experiments. And this, because you have a nucleus that breaks up into two different fragments, and they can have, the fragments can have different identities and, starting from the same nucleus, and they have different energies. The excitation energy gets divided differently, and the neutron emission and photon emission can vary each time. And so Monte Carlo is a nice calculational framework for studying fission as well. So when we started working on FRIA, the goal was to have fast generation of a large sample of complete fission events. And by a complete, we mean we have full kinematic information on all the final particles. Two nuclei, the fragments, they're called products after they emit neutrons, the prompt neutrons, and also the neutrons and photons that get emitted. And when you can sample complete events, we can build a big file where people can just extract any observable that they want. And it includes fluctuations and correlations. So it's easy to say, okay, my detector covers such and such an angle. So I'm going to make a model of my detector covering those angles and see, how many of the neutrons and photons they land in that detector. And then you can see like how long it's going to take you to get enough events to have good statistics in your experiment, or decide, no, I really don't want my detector there. I want to put it over there instead, or something like that. And an advantage of an event generator that's really fast is that you can incorporate it into transport codes and look at a bigger picture than just fission. And why is it important to have correlations? Well, every part of a fission event is correlated. And over here on the left, you see what the average fission model, which is basically you have a blob, and you don't know anything about the initial state. It's just a blob that neutrons and photons come out of. In fact, the MCNP generator developed by Los Alamos, before a code like Freya was included, the way the event was structured, they would emit a bunch of photons, and then they'd decide what kind of reaction occurred, which is kind of backwards. But in these average fission models, the fission is really a black box, and all of the neutrons get sampled from the same prompt fission neutron spectral distribution, regardless of whether it's the first neutron or the fifth neutron. And they would always sample either 2 neutrons or 3 neutrons for say a neutron multiplicity of, say, 2.4 something. So they would sample 2 neutrons and then 3 neutrons enough times that the average would be 2.4, which is not very useful. And those neutrons there don't have any idea about the energies over here, or the energies of any other neutron. So a detailed model like Freya that takes into account energy and momentum correlation conservation automatically includes such correlations. So that's pretty cool. I'm really going slowly, so I should try to speed up a little bit, I think. But just to give you an idea of how Freya actually works, we have fission yields and total kinetic energies that Kyle talked about yesterday, I'm sure. Not yesterday, Tuesday probably. But you sample the charge and mass of one of the fission fragments from a distribution based on data, and given that, plus the incident neutron energy, which is 0 if you have spontaneous fission, then Freya will select the charge and mass of the opposing fragment. It has to add up to the mass and charge of the original nucleus before scission. So we assume binary fission. We don't assume that there are more than 2 nuclei that are emitted in the fission event. So there are some cases where you have 3 nuclei, it's called ternary fission, but we don't consider that right now. But once we identify the fragments, you can calculate the fission Q values based on the mass excess between the fragments and the original nucleus. And then that Q value is the sum of the total kinetic energy of the two fragments moving away from each other, typically back to begin with, because that's conservation of momentum. They start from basically effectively rest, and then they move apart. And we can sample the total kinetic energy from a distribution, but the Q value isn't just the total kinetic energy, it's also the total excitation energy. So the total excitation energy is basically Q minus TKE for a given event. And that total excitation energy, sorry, it is composed of both internal excitation of the nuclei, which is what gives you neutron emission, and also rotational energy, which basically is the rotational energy or the spin that Nathan mentioned. And that gets set up between the two. And but those, both the rotational energy and the intrinsic excitation energy, has to be divided between the two fragments. And we do this based on nuclear level densities. And then we include thermal fluctuations to obtain the final excitation energy sharing between the two fragments. But because we've now changed the energy based on these thermal fluctuations, we have to take that energy away from the total kinetic energy to maintain energy conservation. And what I'm going to talk about in terms of angular momentum, they have spin fluctuations to conserve angular momentum, because there are two types of momentum, right? I said the nuclei are rotating and they're moving apart from each other. So that's linear momentum for they're moving apart from each other, and also the angular momentum for the fact that they're spinning. And if we're talking about say thermal neutrons on a heavy nucleus like uranium, or spontaneous fission of a nucleus like californium, then I don't need to worry about anything else. But if I increase the energy above, say, the threshold for neutron emission, then there's a competition between fission and neutron evaporation that has to be taken into account. And that's what's called nth chance or multi-chance fission. Because if it doesn't work the first time and after you emit a neutron, it may work the second time. So you get a second chance at it. That's why it's called multi-chance. And the general assumption also is that if a neutron comes in, it will equilibrate. That means settle down into the nucleus that it impacted. But if it doesn't, if it just kind of gets caught briefly on the surface and then gets emitted again, that's called pre-equilibrium emission, because it doesn't get the time or doesn't have the opportunity to equilibrate into the compound nucleus. So that's all the setup until fission. And then after fission, like I said, we have these hot rotating fragments that need to lose their excitation energy first by emitting neutrons and then by photon emission. And Freya has 5 physics-based parameters. I mean, we have other inputs as well, like the nuclear masses, fission barriers, the yields and total kinetic energies themselves. We don't generate our own fragment yields within Freya, so it needs to have that information input, whether it's from a model or from data. It doesn't matter, we still have to have it. And the physics parameters are the level density parameter. So when I said the nuclei are hot, they have a temperature. And this level density parameter A relates the temperature to the excitation energy. So that's so at fission, for example, the fission energy is equal to this A times T squared. And this E0 in this denominator here is the first parameter in Freya. We also have a spin temperature, which is fluctuating around the scission temperature according to this other parameter, CS, so that TS, which governs the rotational energy of the fragments, is proportional to the CS times the scission temperature. So that affects the rotational energy in the photon observables. And I mentioned that the total excitation energy gets dissipated through neutron emission. This is total internal excitation. So the statistical energy gets this, which is what is lost through a neutron emission, gets partitioned between the two fragments according to the level density parameters to begin with. But we make a couple of changes. First, we know that the light fragment energy typically is a little bit higher than that of the heavy fragment. So the light fragment gets a little bit extra excitation energy with this parameter x. And this affects the neutron multiplicity as a function of fragment mass, and also the correlations between two neutrons. And we also give the fragments a thermal variance in this fourth parameter C, which basically means there's Gaussian-like fluctuations in the excitation energy, and this really affects the neutron multiplicity distribution and its moments. And then we have a fifth parameter that we call DTKE, because all of this is basically related to the excitation energy, but the TKE is not just independent of everything. We adjust that to some degree to fix the average neutron multiplicity, so it's approximately correct. So we have values for these parameters for every nucleus in Freya, but we did an optimization for spontaneous fission in collaboration with Jackson Van Dyke, who was an undergraduate at UC Berkeley at the time, and Lee Bernstein. And we found out that, we knew already that the parameters C, X, and CS have direct effects on the neutron multiplicity distribution. The neutron multiplicity is a function of mass and the photon observables, and no other parameters significantly affect these observables. So if I vary X, it has no effect on P of nu, basically. If I vary CS, it has no effect on nu of A. But the shape of the neutron spectrum gets affected by all of these parameters, so it's a little bit harder to pin down. So just to show you, these were our optimal values. E0 was a little bit over 10 per MeV. X is a little bit greater than 1, about 1.1 to 1.3, depending on on the average neutron multiplicity to some extent. CS is around 0.9, and DTKE can vary a lot, and the neutron multiplicity parameter here can vary between a little around 1 to 2 or 3, which was surprising. But these first four nuclei have almost just slightly more than 2 neutrons emitted. Californium, on the other hand, has almost 4. So it's a big difference, and it may have something to do with that, because you might expect the shape of the distribution to be very peaked, but these distributions are actually quite broad. And there's not a lot of data sets to fix the data too. Californium has, because it fissions fast and it fissions a lot, you can get fabulous statistics for some observables with californium in an hour. It takes a couple of days to do the same thing for, say, plutonium-240. Um, I already talked about that. So this is how the neutron multiplicity looks as a function of fragment mass and total kinetic energy. It fits the total kinetic energy a lot better. But just want to mention the shape of this is referred to sometimes as a sawtooth. And um, so you, what's interesting here is around 132 um, for the mass number, you see a dip, a minimum in the neutron multiplicity. And this is because it's around 10 132. And if you remember from say atomic physics or chemistry, you know, the electrons are arranged in magic numbers and shells around the nucleus. And you have something called nuclear shells very similarly um, in nuclear physics. And 132 has 50 protons and 82 neutrons. And those are what they call magic numbers of closed shells for protons and neutrons. And so it's really stable. And so its excitation energy internally is really low. So it's not going to emit a lot of neutrons. On the other hand, some of these nuclei over here are more deformed, further from stability, and they're quite happy to emit neutrons. And you see these bars here aren't error bars. Freya doesn't, this is not an uncertainty in Freya. This is just the fact that for any given mass number, you can have a variety of charges that give you the same nuclear mass. Okay, so now here's what I was talking about in terms of the neutron multiplicity distribution. Californium has about 3.7 neutrons emitted on average. So it's got a very broad distribution and it's peaked over here around 4. Plutonium-240 is peaked around 2, but it's really broad. And so you can emit maybe even 5 or 6 neutrons here. But we're looking at some new data now. There's a prompt fission neutron spectrum measurement from Los Alamos, and they're taking more data now. So I'm working with Alex Tuckey from the University of Michigan to optimize the Freya parameters for all the plutonium spontaneously fissioning isotopes with new data. I mean, we're hoping they'll also have data on at least 242 plutonium and maybe 238 as well. And you know, once you fix these parameters for some data, then you can predict different observables to all the data. So I just want to mention, since I talked about correlations all the time, I just want to show a couple of common ones. There's 2 neutron angular correlations and also correlations of neutrons with the light fragment. So over here on the left, on average, for 2 neutrons emitted from plutonium neutron-induced fission here in this case, you see this kind of distribution given by the black line. But this is composed of several parts, right? Because we have two fragments and the neutrons can be emitted from either one of them. So if you have, and of course, you know, fragments can emit more than 2 or more, you know, more than 1 or 2 neutrons, and that has some effect on the shape of this also. But if you detect these 2 neutrons and they're from the same, they're from different fragments, then you'll have a back-to-back correlation and a peak over here at 180 degrees. And if the 2 neutrons you detect are from the same nucleus, then you'll have a peak at 0 degrees. And this, you know, if you think about it, in the rest frame of the fragment, when it's just sitting there, it can emit the neutrons in any direction. But actually, it's in the lab frame, the fragments are moving apart from each other. And so the neutron distribution gets boosted along the direction of the fragment. And so that's why you'll see these kind of structures. And the light fragment, if it emits both neutrons, it's going to be more sharply peaked because it has a higher velocity than the heavy fragment. That's just momentum conservation again. So when you take all of these different contributions into account, then you get the black curve. And if the neutron is emitted, on the other hand, if you have neutron light fragment correlations, then if the neutron is emitted by the light fragment, it's going to follow that light fragment. It's going to be peaked at 0 degrees and nothing at 180. If it's coming from the heavy fragment, then that correlation is strongly peaked over at 180 degrees. But the contributions from all of them look like this. Sharper at 0 degrees, but still a little peak at 180. Okay. So you can study these correlations, and this is in 240 plutonium, and in fact, we could tell already from this that this X for plutonium 240 was about 1.3, because what we assumed originally didn't really match the data very well. So that's how we could tell that X affected both nu of A and the correlations. So now here on this side, their correlation depends on the kinetic energy of the two neutrons. And so you see steeper back-to-back correlations at, say, 1.6 MeV on average for neutrons than at about 0.4 MeV. And it's because there are more neutrons that have the lower energy, and so you'll see a flatter distribution, but there are fewer that would have that higher energy, so you see a more peaked one. And then this is the neutron light fragment correlation for different values of the light fragment mass, and you can see how they change a little bit with mass. So now I want to go to the angular momentum generation. So you can still get spinning fragments when you have spontaneous fission, but you can impart some spin to the problem to begin with if you have neutron-induced fission. And when the neutron comes in and hits the fragment somewhere, where it hits the fragment is called the impact parameter. Sorry, not the fragment. My apologies. I mean the nucleus. And so this defines a plane of rotation, and this plane can change if you emit some neutron before the nucleus fissions. And you can look at all of these papers here and learn more about how we do angular momentum in Freya. But so the mechanism for Freya spin generation is nucleon exchange, and there are different angular momentum modes that have different what you call relaxation times, or the time that it takes to actually equilibrate this mode. And it was started originally based on damped heavy ion reactions in the 70s. This explains the relationship between nucleon exchange and energy dissipation. And then this is built on this theory of transfer-induced transport and damped nuclear reactions. So my collaborator here in Roundup followed this up in the late 70s, beginning of the 80s with these papers where every transfer changes the nucleon number and the excitation energy of the fragments, as well as their linear and angular momentum. And this, in a damped reaction, you have friction, and that's what's referred to as a mobility tensor. And that mobility tensor determines the different relaxation times. And they're really great names. They're wriggling, bending, twisting, and tilting. And wriggling is fast and tilting is slow. So when while the two pre-fragments are still connected, they're exchanging nucleons through the neck region. That's kind of illustrated right here. And the separation between the centers can get bigger and bigger depending on the time. And as you're approaching scission, it's D is bigger than when you're just starting out the process. And the neck radius C is assumed to be, a couple of Fermis at most. So these are the mobility coefficients for the various modes, and they depend on the current of the nucleons in one direction, the separation between the two centers, and the neck radius. So you have these two moving fragments. They're moving away from each other with a total and relative mass. So you can rewrite the kinetic energies in terms of these, the kinetic energies of the individual individual fragments, or you can write it in terms of these total and relative masses. And you can do the same for angular momentum, where you have the spin is determined by the rotational velocity and the moment of inertia. And you can define a total and relative spin and total and relative moment of inertia. So you can rewrite the rotational energy for each of the two fragments based on these S plus and S minus and the total and relative angular moments of inertia. So you have three coupled angular momenta, the spin of the light fragment, the spin of the heavy fragment, and the orbital angular momentum that connects them. And for total energy angular momentum conservation, you have SL plus SH plus L. And because there are three directions, it's a triangle to some extent. I mean, you can write it like, you can call it a triangle with a sum equal to S0. And this S0 is 0 for spontaneous fission. So we have wriggling, bending, tilting, and twisting. That's 4, but wriggling has 2 different directions and bending has 2 different directions, so that's 6 altogether. And you can see how they look here. I won't try to do the hand motions again. But wriggling and bending are perpendicular to the fission axis, and in wriggling they're moving in the same direction around perpendicular to the axis. Bending, they're moving in opposite directions of each other perpendicular to the axis. And tilting and twisting are both parallel to the fission axis, and in tilting they're parallel to each other, and in twisting they're opposite to each other. So we can rewrite these the rotational energy in terms of these different angular momentum modes, and because you have these wriggling, bending, tilting, and twisting modes are introducing fluctuations in the overall momentum. You can write them as that change is delta S for each one and delta L, and you have to make sure that total angular momentum is still conserved even if you can't possibly observe the L, you know it's there. Now tilting isn't really important at all because L dot R is equal to 0, but these three modes, wriggling, bending, and twisting, can be in play. And remember I mentioned the parameter CS? Well, we can try to study the effects of looking at the different contributions of these spin fluctuations by tuning the coefficients and calling them, instead of CM, C or CS for a single value, we can write them in C wriggling, C bending, and C twisting. And in the default value version of Freya, we have full wriggling and bending, and we didn't include any twisting to begin with, but we can try to see like the effect that it has. So how fast are these relaxation times? So you can look at the relaxation times for wriggling in green, bending in blue, and the bending depends on the mass asymmetry. So depends on whether there are two very different mass fragments or the fragment masses are fairly similar. And then twisting. So this is the this blue band here is the fission time. It's between 1 to 4 times 10 to the minus 21 seconds. And the neck radius is between, say, a little more than 1.5 to nearly 3 Fermis. So somewhere, this is where scission occurs. So if the in the yellow region, whether these curves intersect the blue band or fall below it. If they fall below it, then they're definitely fully agitated. If they're somewhere in between, then they're likely to be agitated. But the twisting is less than the bending. So it's a good question, like how much the two how important they are relative to each other. So I will, in the interest of time, skip over this part and go to how we learn about angular momentum based on measurements. So a couple of years ago, there was a paper published in Nature that said there's no significant correlation between spins and the fragments. So if there were correlations between them, then these lines would have a slope, and they're all pretty flat. So the interpretation was, I mean, there's no significant correlation between the fragment spins. And this could be, they interpreted that as the fragment spins are generated after the nucleus splits. And before that, it has nothing to do with what the momentum generation at all. And this sounded like, who cares about angular momentum conservation? But even though total angular momentum is conserved, you can still have no visible correlation when you look at many, many, many different events, because some will be say wriggling in one direction or wriggling in the other direction, or bending, some combination of wriggling and bending, or even twisting that will make the correlation just, even though it's very strong for an individual fission event, on average, it's not very strong at all. So they're only weakly correlated, and there is some recoil that can change the orientation of the relative fragment motion, but this is only like a couple of degrees. And you can see that there's a slight preference for opposite spin directions. So this P over 180 relative to 0 is about 1.2. And this is similar to previous measurements. And the moment of inertia for the orbital angular momentum is very, very um, big. So um, it means that um, this will give you a very weak fragment spin correlation. And you can see here, and also you can see that the average spins are about around between 4 and 5 for the light fragment and a little bit more for the heavy fragment. Um, but the correlation coefficient between the two is very small. So what is the real correlation between the fragment spins? I want to skip this for now and go to this part here. Um, and then maybe go back to that if we have time. So there was a very famous paper by Jerry Willoughby, famous um, in the fission world, let's say, and they studied the angular momentum of the primary products found in spontaneous fission of californium, and this is Willoughby and collaborators, um, and this was their measurement. They looked at this is a function of angle for there's a couple of this is a heavy fragment and light fragment, and they see the kind of correlation you might see over here. Um, this is the angle. This is the cosine of the angle, so it's a little bit different. But the green curve is what you get when the spins are perpendicular to the fission axis, while if they're parallel to the fission axis, like in twisting, then you get that's the red curve. And the observations are consistent with fragment spins being aligned in a plane perpendicular to the fission direction. So that's effectively like a two-dimensional distribution. Yes, I mean there's a third dimension, but it's less important, maybe. So go to back up here. So we can look at we can test the different levels of twisting by seeing how much this oblate versus prolate changes as you change the amount of twisting. And in the standard fryer for californium, you get something that looks like this, which is very much the prolate direction, prolate type. If you take the best guess based on the relaxation times, then you get something very similar. But if you let all of the modes that are active, wriggling, bending, and twisting, be maximized, then you get a distribution that looks very flat. If you didn't have any wriggling and bending at all and just twisting, then you'd get this oblate kind of distribution. So you can get you can change it from prolate to oblate just by changing the amount of twisting relative to wriggling and bending. And then you can see if we tried different different combinations of bending versus wriggling. And you can see here that the amplitude of this relative direction at 0 and 90 degrees can change from about 1.5 to 1.1, depending on how much twisting is occurring. So this is like homework for somebody to go and repeat this experiment by Willoughby and collaborators using modern equipment and a lot more accurate data to measure the amount of twisting that's present. And yeah, just to say this was published in 1971, so it's older than I'm sure pretty much everybody online here. So I've used up nearly a whole hour. I could go back and talk about whether this all has to do with whether we think it's 2D or 3D, and there's a bit of controversy about that. And I can talk about it more if you want, but I think maybe in the interest of time, I should take questions first.
That sounds good. We do have a couple questions in the chat.
Yeah, I noticed a couple of raised hands or things coming in, but I didn't, I just wanted to try to go through everything first. So
Mhm.
please.
All right, so the first question is about angular momentum conservation. It
Mhm.
reads, how can we assume that the three coupled angular momenta are conserved if they're not about the same axis? Do we assume that the axes are parallel?
No, I mean, you can, the spins can point in any direction. They just, yeah, they just have to add up to the total spin of in the problem. And if it's spontaneous fission, it's zero, right? I mean, the spins have 3 dimensions. I mean, you can say, say, okay, if the z-axis is the fission axis, then they're going to be perpendicular to that. But it doesn't have to be. But you can still anything that where you can make the momentum vectors add up is possible. And that kind of goes back to this correlation between the fragment spins that I didn't really talk about. But yeah, you can if you want to, you can think about it and maybe more easily on fewer dimensions, but yeah, it's the same as um as linear momentum. I mean, you have 3 vectors for each linear momentum, but they'll still add up to zero for momentum conservation.
Great. Another question, how do you differentiate between photons emitted due to fragment de-excitation and those from other processes?
Uh, what other kinds of processes? Um,
This might be a more experimental question.
um, you can ask the same thing about neutrons, right? Because neutrons can bounce off the walls and create different, a lot of background. But the you know, uh, I would say that that's a good question for an experimentalist like you, Nathan.
Aha. Uh, so how do you differentiate? The answer is you can't always differentiate event by event, but the hope is that you can understand your background well enough to quantify it and subtract it from your total measurement.
Yeah, I mean, that has to do sort of with detector calibration for one thing, I guess. The one thing you can do is like do a target in, target out kind of measurement, right? And get some idea of the ambient background, right?
Mhm.
Um, and uh, yeah, I'm not sure about anything else per se, but yeah, we have it kind of easy. I mean, like some of the high energy experiments or even um I mean they look at things like muons and neutrinos and um to get the calibration for cosmic rays from muons going through their detector, they just yeah, they watch and see, you can see the muon tracks go all the way through from one side of the detector to the other. And if it does, so that's very different from coming from a specific vertex, but you don't look at photon tracks kind of the same way as you do those kind of tracks. Um, because they don't they're not charged, for example. Neutrons and gammas are really hard because they're not charged.
Indeed. All right, we have a couple more. This is everyone's favorite. How is this understanding of fragment correlations applied to practical applications?
Oh God. Um, um, well, um, I mean, I think a better understanding of if you really want to know like um something for specific for nuclear nonproliferation, um, that's a that's a little bit harder of a sell, but if you put it in terms of trying to understand really, the photons coming from fission to do some kind of like passive detector analysis or something, then you need to, or active interrogation or whatever, you need to know, um, you need to have a good understanding of the physics of fission. And just one totally different example of how, um, but related to like how, you know, fundamental physics can really play a role in understanding stuff. I mean, people want to use neutrinos for reactor monitoring, right? So there there have been some experiments that watch neutrinos coming from, or antineutrinos, coming from reactors, and they realized that this this number of neutrinos was very different from what they expected, and they to try and solve what they called the reactor antineutrino anomaly, they had to look deeply into understanding the neutrino, the beta decays of specific fission fragments. So if you're, trying to monitor a reactor for, using antineutrinos for some kind of, um, security purpose, then yeah, I mean, the fundamental physics is really important. So, I mean, it's, you know, understanding the fundamental relationships between the fragments can help you understand, how the photons come out from a fission event the way they do, and how they end up in the detector. That helpful?
I think so. All right, we should probably stop there. Thank you very much, Ramona, for another great summer school presentation.
This is fun. I always enjoy it.